All right, so let's play with this thing, shall we? If you haven't watched the video before this one, go watch the previous part where I go through basically this diagram, seeing exactly how the thing works and my plan for what we're going to do here. So before we even start, and the first thing I want to do is to use whichever self-calibration mechanisms I have in the thing to calibrate itself. And one thing I can do, according to the book, is to calibrate my VU meters. And the thing's upside down because the board's on the top side over there and I need access to the pots. And it's generally just easier this way, so sorry for this, but it is what it is. Here's the idea. It has a built-in, you can't see that, it has a built-in, it's called test oscillator, it says that right here. So this is a 1 kilohertz signal. And actually, in fact, this is the very first calibration that you do. So you set your output to SRL, right? Because it will be within the ballpark. It doesn't actually matter. This doesn't matter because all we're trying to do is we're trying to, on a diagram, right? Signal coming out of here is going to be plus 4 dBm, right? There's no pots in here. All the pots are here. So, and that same 4 dBm signal is going to go down, focus, down here, and it's supposed to show up as 0 VU on the VU meter, according to the book. And so that's what we do. We basically, so that's my line output. I just made these plugs that I can put the hooks on, right? And we're talking about a sine waves RMS voltage here, right? So you can say, so such and such here. Okay, so let's just put this to volts AC, and I'm just gonna, put some volts on. See, so like what you can say 1.2 volts AC, 1.22 volts AC. Well, or you can say dBV, or you can say dBm. And this video is not about dBVs and dBms. Quite frankly, I'm still myself a little fuzzy. I'm not yet ready to explain them, although I understand them enough to be dangerous. But basically, it's just think of this as a unit conversion, okay? If you can say some millivolts, volts, or whatever, you can say that they're dBms and dBVs. So what I could have done is I could have written down some key dBm numbers and just mapped it. But I'm going to cheat because this guy very conveniently can do that. Ha ha ha. Get one. eBay, $200. This is, this used to be my main meter. Tangents used to be my main meter. I don't use this anymore. Costs about the same amount of money, and this is so much more powerful and quick. That I prefer that. At any rate, so let's see. So here's how you do it, right? So you configure the thing to basically put your test oscillator in some. Test oscillator is a part of the input circuitry, right? So you're gonna go here, 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 and here. This is the input side. Watch the previous video. So I have to configure it properly. So over here, instead of listening to tape, which is in, I'm going to listen to source, right? I'm not going to record anything. And now when I press this guy, see, these guys jump, and that signal gets put out of my output. Oh, looky here, 4 dBms. I already set it up for 4 dBms. Now, if the level wasn't correct, you would adjust those knobs to tweak the level to show you 4 dBms output. Now, what's supposed to happen is my VU meter, which in this case, I'm currently hooked up to channel number, let's see, this is 2, this is 1. So I'm currently hooked up to channel 1, right? Oh, and I lied. This is 1, this is 2, so it's this guy. So this guy, 4 dBms over here, shows a little bit over 4 dBms, right? So over here, there are these trim pots accessible through those holes. And the one we're looking for is VU meter calibration. So we're on channel 2. This is R186. So I'm going to set you somewhere where you can see the VU meter, and then, because I need two hands. I need one hand to hold the button and the other hand to tweak the pot. So take my trusty flat blade and so test oscillator, and then I need to find the 186. That's it. Found 86. Here's 186. Don't short anything. No, I'm not supposed to use a flat blade screwdriver. Okay, so let's see. Should move. Oh, that's the wrong meter. No, what are you screwed up? Channel 2, yeah, 186, and I am on 86. Oh, yeah, channel 1. That's right. I'm on channel 1. I'm stupid. Okay, so 86. Because the thing's upside down, I get confused as well. Okay, so now the other one should move. Okay, there we go. So we're still at 4 dBm on the meter. And this is about, so see, I can adjust it. So this is about 0 right here. Very touchy. Okay, so this looks good. Now, same thing with the other channel, right? I'm not gonna bore you. It's supposed, I checked it before starting the video. I think it's gonna be about right. So, oh, come on, don't do this to me. 4.3, okay, well, I guess I have to adjust. So, I'm gonna adjust the input level to be 4.0, right there. And my VU meter is just a hair below 0, so I'm just gonna move that meter up. That's down, up. So right about here. This is pretty short, so I'm just trying to get them in the ballpark. I'm not trying to make them any perfect or anything like that. Okay, so now we know that 0 over here corresponds to 4 over here. And that's the end of it. And we're just going to use these as a quick eyeball to make sure we're not cooking the thing, right? Now what I'm actually going to do is I'm going to switch off the standard reference level, and now this pot that controls the output level becomes active, and now I can see I can start the signal generator. And oh no, sorry, never mind, I cannot actually adjust signal generator with this guy, but I can adjust the input. Now remember my idea where I said, okay, I'm going to drive the head with negative 50 dBms, and I'm going to see if I get positive 4 dBms over here. Now, let's see. So these are, right here, the wires that were connected to the left and right channel off my repro head. And all I did was I put some RCA jacks to them. Just very nice. The head's off, right? So I was able to do this. So now I can plug something in here, and that essentially is my head. Right? Just goes straight through the thing. Here's the problem. I don't have a signal generator. And like, think about it. Negative 50 dBm is pretty low, right? It's really close. Well, it's halfway to, but it's a very, very low level signal, right? It's a signals of millivolts, if I remember correctly. So I don't have a signal generator that can do that well. And actually, my audio analyzer does, but it's close to noise level of the audio analyzer. And regardless, so I decided, after playing for a little while, I decided I'm going to do this. So this little terminal strip, all it is just a very simple attenuator that's adjustable, right? So what I can do is, so what it is it's this, right? So this is your ground. And this is your input. You can see it, right? So this is input, right? So supposedly you have this here, and you got a pot in here. And this is your output. That's all it is. And there's an RCA jack right? Connected like this. And so the idea is you're gonna, hook up your source here, and then you're gonna take this and patch it to the heads. That's it. So, because I have two heads and two sides, I have two patch cords, right? And just options. They're the same. And this is my attenuation pot, and this is the input. So let me set this up with a scope, and I'll unpause. Okay, so here's what I've done. My scope signal generator, which we're going to be using for now, goes into my input of the attenuator, and the output of the attenuator is not even hooked up. I just hooked up my fancy multimeter to it. And what I want to see is before I even connect it to the downstream circuitry over here, which actually will put it through the amplifier, I want to make sure that I haven't screwed anything up in the sense of my signal levels, right? Because I don't want to fry the thing. So I'm going to be very, very careful here. So what we're going to do is we're going to go to the generator, to the scope, and turn the wave generator on. And now we're making something, and it's a sine at 1 kilohertz. And what I'm going to do is I'm not going to care for what the amplitude here is, which I can adjust. What I'm going to care for is I'm measuring what I'm going to send over to here, right? So I'm going to go and make sure that this is 50. See, right now it's negative 70. So I'm going to make sure it's negative. I'm increasing the output voltage of the scope. The current amplitude is about 148 millivolts peak to peak. So I'm just bumping up the voltage on the scope. Scope's output. Scope's, well, technically it's the generator output, until I get my actual signal that's going through the attenuator to be about 50 dBm. Coming close. Oh, not too much, sorry. Right about here. 974 millivolts, so almost a volt. I mean, right now it doesn't matter what this attenuator is doing. It's just as long as I have negative 50 on here, which is what I'm measuring. Okay, so now I'm relatively confident that I'm not going to fry anything in it. And the very first thing I want to confirm, this is now off, no lights are lit. The very first thing I want to confirm is I want to pretend I'm playing this signal through my head, right? So I'm going to stick this signal into my left channel, which is, I believe, what, left? This guy, because it's upside down. So this goes into the left channel. So when we turn this on, roughly, we should be capable of producing, remember, 4 dBms on the output equals 0 on the VU meter. So we're going to leave everything as is. And we're going to get to 0 VU. Now, here's what I did. I turned this off, and I'm going to use this to slowly bring the signal level up, just to be safe. So, power. Now I'm waiting. So now, let me see. So I'm going to bring this up. Oh, yeah, of course. So right now I'm monitoring my source, right? Remember we were just doing the test with the test oscillator, so I could do that. But I don't want to. I need to monitor my tape now. And I also need to tell the thing to pretend the tape's in there. It's that lever. It just turns the whole tape circuitry on. So now, if I start, yeah, there we go. See, it's coming up. There you go. That's my 0. Right there. Now here's an interesting thing that happened. You see how that went to negative 29? So this probably has to do with some loading that the downstream amp actually causes. Or no, actually, wait, no, loading. Why did the signal level went higher? It was negative 50, wasn't it? Okay, that's interesting. I actually can't explain this. Oh, crap, I'm a moron. Of course, the signal level went higher because I disconnected my stupid meter. I can't explain it if I think about it for a second. So what I found was that the reason why I disconnected the meter, and I'll do this automatically, is what I found it when I started doing like more interesting measurements, the meter connected actually negatively affects what's going on because this is such a high sensitive circuit and the signal, yeah, it's 50. Signal levels are so low. When I have my meter connected over here, or even if I have my scope connected over there, I start getting some weird harmonics and whatnot. We'll see harmonics later when we look at the audio analyzer. So yeah, I just automatically disconnect the meter, and I confused myself over there because it's picking something up from the air. Actually, as you can see, my quote-unquote air garbage that's flying in the air is negative 29 to 30 dB, which is higher than what the head's producing. And if I short these though, I should go to the noise floor. Yeah, which is like 120 on this meter, at least just like this. Anyway, back to this. So this is promising. I put in 50 dBms in here, and I managed to actually, seems like it's outputting something. So let's see what it is outputting, right? So I'm gonna go hook up the scope probe and be right back. Well, and all I did was I hooked up this probe from the scope to the output of the deck. And looky here, our beautiful, beautiful sine wave. Pretty cool. But I can immediately see that something's off. Do you see how it's jiggling? Let's zoom out a little bit. Uh-oh. So that was the first thing that I see. Do you see this? So there's a sine wave fundamental, but there is some weird thing that causes it to do this. And when I'm going to put it on the audio analyzer, you guys will see this is actually a 60 hertz component, which is extremely bizarre. At least for now, it's bizarre for me because power supply noises, from what I know, are 120, not 60, but it's 60, and I don't know where it's coming from. But I think I've proven my point that I can take this thing and pretend that my signal generator is my tape head and analyze it that way. Now here's the other cool part. I can actually look at the signal generator output. That's the signal generator. I'm pushing this test button. Remember when we were using, so that's an internal 1 kilohertz signal generator. Let's look at this signal. Let's see how good it is. Oh, do you see? Do you see what I see? Just zoom out a click. Maybe make them, sorry, I need more than 2 hands. Nope, too much. Yeah. So I don't know. I see some curvature in the front edge of it. Like this button, I have to keep pressing in order for it to work. And I'm not gonna go tape it right now or clamp it. Sorry, I'm lazy. But the shape of these does not look quote unquote proper. For like, you see how it's maybe tilted a little bit in the back direction over there, the crests, the tops. So this is interesting, and this is going to be interesting to find out what's going on with this and why. But hey, just fun. You know, I can make sure my test oscillator works. So the next thing I'm going to do is I'm actually going to use this guy which is basically an audio analyzer. So what is it? It's a spectrum analyzer that has a very, 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 very low distortion signal generator. No, it's not. Okay, all right, fine. This is like a $400 little consumer grade slash hobbyist grade thing. It's nothing super, right? But it has like pretty decent signal generator, way better than this guy for sure. And it can do sweeps, and it can do FFTs, which is spectrum analysis. So we can see components and harmonics, and we can also do some harmonic distortion analysis. So the next thing we're going to do is I'm going to hook this up as a source and a scope to this guy, just in the same manner, and come back. Okay, so at this point, everything's hooked up. Basically, the signal generator of the audio analyzer is hooked up to my input, and the back side of the output, I used my XLR cable that I made, is connected to the, oh, that's a power cable, excuse me. This guy is connected to the input, and I guess I should move the power cable out of the way. So I'll do that, and then the rest of this analysis, I'm actually gonna, because there's gonna be nothing happening over here. All of the stuff's gonna be happening over here. So I'm going to record the rest of this off of my computer and walk you through what I'm doing. Okay, so now we're on my computer and it's hooked up to my audio analyzer. And what I'm having here is I'm feeding it the same setup, right? So it's 1 kilohertz, and that attenuator in the machine is set up so that 0 dBm over here, and dB and dBm in this particular context is the same thing, is equal to -50 on the head input, right? So it's gonna basically just zeros everything at 1 kilohertz frequency, and it just makes it easy, right? So we're looking at this is a spectrum, right? So 0 is my fundamental, and then remember what we're seeing, it's like this funny wave shape happening in my scope. So you can see that's that component number 1. That's a 60 hertz component, and it's pretty big, right? And the next one that's also pretty big is this 180 hertz component. And then my power supply hum's right here, which is actually -62. So it's what, like -68 below signal level, which is annoying, but whatever. So these are interesting. I don't know what's causing them. By the way, so what I'm going to be doing, right, is as I rework the thing, I'm going to keep doing this now, and I can see, I mean, ideally, I'm going to start losing some of these weird extra components in there. And these are all my harmonics, and obviously I can see my total harmonic distortion noise, total harmonic distortion without noise, but like this is the interesting number, right? So then the next thing I did it yesterday before recording this video, right? Is what I did was I was like, all right, so let me look at the thing, right? I'm just gonna sweep it. I swept it from, I want to say like 20 hertz to 20 kilohertz, and I did a response little graph. Now, here's a response graph. So what's funny is, well, why is it not flat? Well, remember we were talking about equalization in the video before this one, right? So there has to be some equalization. And for NAB, which is what this thing is, it's a NAB equalization standard. This looks about right. Again, right? Like I'm overdriving it over here, right? You see how it's like outputting. So sorry. Do you see how it's so this is my kilohertz, right? This is my four dBms right here. But over here, see, it goes all the way like to what, about 17 and a half. So this is in the overdrive region for the amp. In order for me to actually sweep it properly, what I need to do is I need to adjust my input signal level to vary, right, based on the frequency, which is what I did. I can't do it automatically and build a beautiful graph like this, but I did it manually, and I did it with, doubling of frequency, basically octave by octave. And this is what I arrived at. So first of all, this is roughly the curve. Okay, like sorry, Excel graphing, I hate it. I didn't even try to make this graph nice, but this is the theoretical graph of what I should have. The numbers have been taken from the internet for NAB equalization curves, right? So the corner frequencies are 50 and 3180. So between nothing and 50, and there's another NAB curve which looks more like this. So in this one, you can see 10, 20, 30, 40, 50. So the peak is right here. So this actually is what I have in the thing. And this is a different version of this curve. I think this is a newer version when they were trying to standardize stuff. But regardless, over here, I'm just looking for distortion numbers, right? So like even if I'm a little off on the low end, it's like, it's okay, right? I'm just looking at the big picture stuff as long as I keep doing my tests in the same manner. Okay, so at any rate, so I'm just going to use this curve, or rather I use this curve. So look at just these two for now. This is the only thing that matters. So my first pole was at 50 right here, at which point we start going negative 6 dBs per octave, right? Until we reach 3180, and after 3180, we stay flat. That's basically that's the deal, right? Now remember, our initial setup was 1000 hertz at 0. Now, if I start at 0 over here, then by the time I get to 1000 hertz, I'm going to be at negative 25. So what I decided to do was I did it aligned. I just recalculated everything so that my 0 point is here, right? And it's just essentially, and these are the numbers I should put in my generator. Okay, so if I want to put in 0 dBms at 1000, then with this curve, I need to put in negative 25 and a half at 1 hertz between 1 and 50, and then 6 hertz less until we reach 3180. And then after that, I collected these numbers. So first of all, what I was just looking at is this is my output, right? So I was looking at rough. What I don't want is wild numbers over here, right? So this is 2. This is like what, almost 4. This is a little over 4. This is a little more over 4.5, 4.5, right? This is so on. These numbers are within ballpark. As long as I keep repeating the test at these exact numbers while my attenuator is calibrated at being negative 50 dB on the head, into the head, when the generator is set at 0, I can keep rerunning these numbers while changing the circuitry. And hopefully this column is going to improve. And this is the idea. This is what I was trying to do. This is what I was trying to do. But there is another little thing that I was going to show you, but I need back to my phone to do that. So why did I do all of this nonsense? The heads and whatnot. Can't I just, why do I have to do this? Can't I just very simply purchase a calibration tape and a couple of albums and make sure that they sound good and call it a day, Well, here's a problem with that. First of all, calibration tapes are super, super duper expensive, right? And I cannot, it involves the trade transport. And I don't want to like sit there and run my calibration tape for hours while I'm trying to debug stuff upside down, poking my scope probe on various boards and things like that. It's a lot easier like this, right? Signals produced by a signal generator. It comes. That's a very nice album. Come a lot cheaper, right? And they don't involve the transport. So I have completely isolated my electronics, reproduction electronics in the machine from the mechanical and the magnetic aspects of this reproduction in the heads. So that's good. I think that's good. I think that's a win. I don't think this is a very redneck way of doing it. I think I've never heard of anybody doing it this way, but hey, I don't think I'm damaging anything. And yes, so the interplay, because heads are magnetic, excuse me, they're inductive, right? So the interplay between the internal guts and the heads is different than the interplay between the internal guts and my signal generators. But that's not very relevant. I mean, I'm comparing what I start with, which are those numbers I showed you on the computer, with where I'm possibly going to get. So we'll see. We'll see. And maybe I'm a moron. But here's the best part. That's my vinyl table, right? And the output of the cartridge is very close to negative 50 dB. So here's what I thought. The proof is in the pudding, and the pudding's in the eating. Right? All those signal generators, can't they just listen to that through this, using it as my phono preamp? Since the voltage levels are about the same, it should work. Now, the equalization is going to be off. Why? Because the nab curve is a little different than the RIA curve, but it's close enough. It's not reverse. And so I tried. So look. This wire comes off of my phono cartridge. This box is just an A/B testing box. So if I click this way, it goes like this. And if I click that way, it goes like that. Right now, we're going here, which goes to my, what do you call it? Sorry, cartridge preamp. And then it goes into my amp. Okay. So if I click it this way, it's gonna go through here into my head inputs. And then come out of here and go into my amp. So what I have to do A/B testing is just flip this over here and switch the different input on the amp. And it works. Can you hear it? And it actually doesn't, despite all of those crappy harmonics that we found and the weird stuff and the distortion, it actually doesn't sound terrible. And my VU meters are moving. Oh, the song just stopped. But I think this is cool. So this is going to be the final kind of like listening test. I did a little bit of A/B listening tests like this. I can tell that my regular tape head preamp is better, but it's not like, if you go from a cheap solid state amp into a well-made tube amp, you'll like hear the difference instantaneously. If you go from, prefer analog sources. So if you go from, like to me at least, right? If I go from a CD, like regular CD to vinyl, it's a massive difference. Here the difference is a lot subtle, but I can hear it almost, I don't know. We'll see. We'll see what happens when I upgrade it. Or rather, when I at least replace all the old capacitors and all that stuff. But it's sounding surprisingly good. It's sounding surprisingly good. And so with that, this redneckery is probably over. The next thing I decided to do is, so this board is the signal generator and the line amplifier, that last stage amplifier. The equalizer is right here, and this is the record circuitry over here. The power supply is vertical on the opposite side over there. So I decided the next thing I'm going to do is I'm going to carefully unwire this board. I'm going to pull it out. I'm going to set it on the bench, and I'm going to do audio analyzing on this board only. And what I want to see is, I want to see if anything changes when I stop using the power supply that's built in versus the power supply that I have. This board is 18 volts, so I should be able to just give it good, clean 18 volts. And I'm going to use this board as a reference for my changes. I'm using this deck not only to restore it, but I'm also using it to learn. This is probably my first project where I'm actually trying to analytically approach these things. So like one thing I wanted to do is just run it through the audio analyzer by itself. Oh yeah, and this board does not have equalization problem, so I can sweep it automatically. See what my distortion numbers are. Then let's say replace all the caps on one side, because it's a 2-channel board, right? Replace all the caps on one side and see if it gets better on my audio analyzer. If I can quantify it, right? And then do the same thing on the other side. I also want to see if, I don't know, I'm leaning towards trying replacing resistors on one side just to prove to myself that the amount of difference they're going to make is going to be so marginal that it's irrelevant, but we'll see. You know, and things like that. So I'm going to use this as my device under test to prove also power supply, right? So right now, power supply does something. So we're going to look at this board with the power supply as it is. Then we're going to go replace all the capacitors in the power supply, plug this board back into the power supply and see what happens. So that's the plan going forward. It's probably going to take a while because, you know, I'll spend a bunch of time fiddling with the board before I have anything interesting. So for now, that's it.